Hi, I'm Liz and I'm going to be doing the Transport to Exam 2 question. Sorry, I don't have my headphones. I left them at my friend's house, so I hope that you can hear me okay. But I will check to make sure. So, in this problem, we have a cylindrical pipe. I'm going to draw that. We have gas in the pipe. And then we have liquid flowing down the inner walls of the pipe. So liquid. And we have these two guys named Sherwood and Gilligan, and they established a correlation for the evaporative mass transfer of the liquid in this situation. So that equation is Sherwood's number equals 0.023 of Reynolds number to the point, is it 0.83 or 0.86? I believe it's 0.83. Times Schmidt number to the 0.44. I'll check that to make sure, and then I'll probably redo the video if it's wrong. But anyways, so that is the correlation for the evaporative mass transfer of this liquid. And also this is only valid for the Reynolds number being between 2,000 and 35,000, and the Schmidt's number being between 0.6 and 2.5. So keep that in mind. So the first thing that we are wanting to do here is to do a dimensional analysis. And we want to do this to kind of prove and make sure that this correlation or the dimensional groups in this correlation are correct. So like the Sherwood's number, Reynolds number, and Schmidt's number. So we want to establish that the dimensional groups are appropriate for this correlation. So to do the dimensional analysis, first we want to display all of our variables that will be needed in this situation. So we have the mass transfer coefficient, which is going to be represented by Kc, the velocity, the density, the viscosity, the diffusion coefficient of the substances, and there's one more, the diameter. So we have all of our variables, so let's write down the units for these variables. So we have the mass transfer coefficient and the velocity are actually the same unit, and that's meters per second. We know density is mass over volume, so that's going to be kilograms per meter cubed. Viscosity is kilograms per meters times second, the second on the bottom. The diffusion coefficient is meters squared per second. And the diameter we know is just meters. Excuse me. So now we're going to do a dimensional matrix. So we're going to just like rewrite all of the variables on the top here. And then we're going to write all of the base variables along the side. So basically we're just going to write the exponent for that unit, so it'll kind of make sense when we start doing it. But like for example, for mass transfer coefficient and for velocity, meters per second, meters is to the power of 1, and second, since on the denominator, is to the power of -1. It's like writing m to the 1 times s to the negative 1 is the same thing as meter over second, we all know. So, like I said, mass transfer coefficient and velocity are going to look the same here. So we have meters 1 and seconds is negative 1, and then kilograms is not in the unit for those. For density, we have kilograms on the top with 1, and then meters cubed. So that's on the bottom, so that's negative 3 kilograms per meter cubed, and then there's no seconds, 0. Then for viscosity, we have kilogram on the top, which is 1, meters on the bottom, and seconds on the bottom. So both of those are going to be negative 1, and they're just per meters times seconds, so it's just negative. And then for the diffusion coefficient, we have meters squared, so that's positive 2, it's on the top, and then a negative 1, because there's seconds on the bottom, so that's negative 1 per second. No kilograms, so that gets a 0. And for diameter, meter gets a 1, and kilograms in second gets 0, because it's just meters. So next we can introduce this equation, I equals n minus r. So yeah, so I is going to be the number of dimensionless groups n is going to be the number of variables for this situation, and then r is the rank. So I'm gonna dive more into rank when I go to the coding part to show how you take this matrix and you can get the rank in Python. And also I wanted to say that, like, we know, like, we have the number of dimensionless groups and the number of variables that we're, like, aiming for. So we're hoping that the number of dimensionless groups is, sorry, I'm getting a phone call and it's distracting me. We're hoping that the number of dimensionless group is going to end up being 3. And we know that we used 6 variables. So we're hoping that the code is going to give us a rank of 3, because we want the number of dimensionless groups to say 3, because we want this correlation to be correct, and it uses 3 dimensionless groups. So we can kind of check our work when we do the Python and see if the rank is going to equal 3. So I'm going to scoot over to the Python coding now. Okay, so like I said, I'm going to show the Python part now to find the matrix rank. So I pulled the screen up from my tablet, and now I have the split screen to show the matrix and the work that we just did. So first we're going to import numpy so that we can pull from the numpy package in Python, which has, like, more complex functions and things like that. And I'm going to name it np so that when we call on numpy, we only have to use np instead of write all of np. So we're just going to shift enter that, which runs it and imports numpy. Next, we're going to call the matrix something. We can call it something as simple as matrix, but it can be any variable. And then we're just going to, like, type out the matrix. So first we're going to be numpy.array to be able to type out the array. And then I just kind of remember that you need 2 square brackets at the beginning and 2 at the end, just so that I don't make a typo and get an error. But that's because you have a bracket enclosing the whole matrix, and then you have a bracket enclosing each row. So in the matrix. So let's start out here. So if you can see my mouse, the matrix over here, which we did in the first part, and so I'm just going to type it out like we have it here. So gonna separate each one by a comma. So that's the first row. So after the first row, we want to put a bracket, and then a comma, and then I'm just going to enter it to make it look like the matrix that we have in a nice little like rectangle. So the next row is 1, comma, 1, comma, -3, -1, 2. Again, oh, I need to have my opening square bracket here, and then comma, enter, have another square bracket, and then the third row, which is -1, -1, 0, -1, -1. And then we need that closing bracket for the whole matrix. So then I'm going to need to find a function for the rank, because we want the rank for the matrix, for that I equals n minus r equation. So let's just open Google and search for, which is in my search history because I already did this, but we can search for NumPy matrix rank to find a rank function. And this first one, if you read through it, this is what we're looking for. So it's linalg.matrix underscore rank. And we have to pull from NumPy first. So let's go back to here. We have np.linalg.matrix underscore rank. And then we just need, like it says here, we just need what our matrix is called. So we just called it matrix. So I'm going to shift enter to run it. Oh, and the issue was that there was no comma there. So it was showing a 10 and it wasn't the correct matrix. So let's rerun it, shift enter. And now we get a 3. So I'm just going to pause it so that I can pull my OneNote back down to my tablet. And I can write out that the rank is equal to 3. But, so just give me a second and then we'll move on to the next part. How do I Alright, so we're back to our notes here. So we found that the rank is in fact equal to 3, which is good because we're kind of proving out that this correlation is appropriate and makes sense. And we know that it has 3 dimensionless groups. So I'm glad that the rank was 3 because we have 6 variables. 6 minus 3 is equal to 3, which is the number of dimensionless groups here. But kind of for this next part, let's pretend that we don't know what this relationship is and that we're trying to figure it out. But it's kind of nice that we already know what it is. Gillen and Sherwood figured it out and they're pretty smart. So we can use it to check our work and make sure that we are doing it correctly. But, so we got 3 dimensionless groups. So now we are going to figure out what those dimensionless groups are, even though we already know them. But like, let's figure it out. So, this is the Buckingham Pi. I wrote this down, I think I wrote it down off camera from a different take, but this is the Buckingham Pi method to solve for the dimensional analysis. So, I think I meant to write this next to dimensional analysis, not next to matrix, so like ignore this, but whatever. So we're going to solve, we're going to find our pi groups. So they're called, we have 3 dimensionless groups, so we're going to do pi 1, pi 2, and pi 3. So even if we didn't know this correlation from the get-go that Sherwood and Gilliland figured out, we know that it's 3 dimensionless groups because I is equal to 3. and we know that from the number of variables and the rank. So we need our core groups first to be able to find our pi groups. So our core groups are 3 of our variables. So I'm going to choose the mass transfer coefficient, which is a good one to choose because you can determine it experimentally. Then we have the velocity because it's the same unit as the mass transfer coefficient, so it really works out because then we don't have to do as much work later, which you'll see how it cuts down on the work, but it's because they're the same unit. And then we can do the viscosity. So for our pi group equations here, let's just write out them using our variables. So basically, each one is going to get one of these as the coefficient. So I'm going to write those out, the 3. And then we multiply each of those by the other 3 variables to a certain power. We're going to raise it to the power so that it will cancel out the units so that it ends up being a dimensionless number and it doesn't have a unit. So it'll make sense in a second. But basically we have this Kc, the mass transfer coefficient times the density, to a certain power. So we're just going to go through the alphabet for the variable names for the power. Just write it all out for you. Oops, not row. I meant to do. Erase that. There it goes. Diameter to C. And then row. Sorry, I know that looks not like the row above it, but okay, so we wrote them all out. Like I said, we're just multiplying it back to the other variables to a certain power, so that we can then cancel out the units using those powers to create a dimensionless number. So to be able to figure out what these powers are, because right now they're just A, B, C, D, E, F, G, H, I, not very helpful. To figure out what those are, we are going to set it up so that we then solve out a system of equations. So first let's write out what our units are with the equation that we have set up here. So our mass transfer coefficient is meter per second, which we know from right here. All of them are still written out, so we can reference them if we forgot or anything. The density is kilograms per meter cubed. The diffusion coefficient is meters squared per second, and the diameter is meters. So to do this, we're going to write out our base units, so meters, kilograms, and seconds, and then we're going to have 3 equations, and we can solve a system of equations to get A, B, and C for the first one. So we're going to do this for each, we're going to rewrite this out for each of these 3 equations to find what those exponent variables are going to be equal to. So here we go. So we have for the mass transfer coefficient meters per second. So meters on the top, so it has an exponent of 1, and that's the coefficient, so it's just going to be a 1. Then we have, oh, I almost wrote a plus, but it's actually a minus because the meters cubed, that's a 3 on the bottom, so that's a -3 for the exponent. So -3 A, so that's our row, or our density, which is the first exponent here, and then plus 2b, because it's meters squared, so positive 2 exponent, and then plus c. There's no coefficient because it's just an exponent of 1. So I guess there is a coefficient, it's just that the coefficient is 1, so I'm not going to write it. And then that's going to be equal to 0, so that we can solve out our system of equations. Then we can see that the only one with kilograms is our second term here, kilograms per meter cubed. So that's going to be just A equals 0, because it's kilograms like to the first power, so 1 equals 0. And then we have seconds, so the first term, the seconds on the bottom, so that's a negative 1 exponent, so negative 1, and then nothing for the A, and then minus B equals 0, so we can solve that B equals negative 1. So we have A equals 0 and B equals negative 1, so now we can solve for C in our first equation here. So we can just rewrite this as 1 minus 3 times 0, so that's just going to be 0, plus 2 times negative 1, so negative 2, plus C equals 0. So like I said, this is just 0, this is negative 2, so 1 minus 2 plus C equals 0. So then we get negative 1 plus C equals 0, so C equals 1. Great. Alright, I was just kind of mentally checking everything, but so now we have A equals 0, B equals negative 1, and C equals 1. So let's just keep note of that and rewrite our first pi group out. So it's going to be the mass transfer coefficient, density to the 0th power, which actually I'm just going to write that out as 1. So I'm not going to write it at all. And then the diffusion coefficient of AB to the B is negative 1. So since that's DAB to the negative 1, that means that the diffusion coefficient is on the bottom because the negative 1 is a negative exponent, meaning it's on the bottom there. And then the diameter to the power of C, which is 1, so that's going to be on the top. Alright, so we have our first pi group here, pi 1, and we actually know that this is equal to Sherwood's number. Yes. Alright. So then, let's make a little more room here. Next we have pi 2, and actually since the velocity is the same as the mass transfer coefficient, it's all going to work out to be the same because it'll look the exact same as this. So when we write out the base units and all of this stuff, it's going to equal out so that A equals 0, but in this case it's going to actually be, sorry, I'm still not good at using this tablet. It's going to be D because we have D in place of A over here. So D is going to be equal to 0, E is going to be equal to B, which is negative 1, and F is going to be equal to C, which is 1. So it's all going to be the same, so we know that pi 2 is going to be 1 minus instead of, it's not all going to be the same because the coefficient is different. We're using velocity this time, but otherwise it's the same. So it's going to be velocity times the diameter. Sorry, I like make my d's different every time. So there we go. Over the diffusion coefficient. And we know actually that this is Peckold's number, I believe that's what it's called. And I believe that that's the short, like the abbreviation for it, PE. So yeah, that's pi 2, and then pi 3, we're going to have to work it out. So we have mu, which we wrote up here, it's kilograms per meter second. So kilograms per, I'll scroll up so you can still see our pi 3 equation. Kilograms per meters times second. And then it's all the same stuff again. Meters squared. Sorry, I get sloppy when I have to rewrite things. Alright. So let's do our meters, which is meter on the bottom, so we have -1 minus 3a. Well, sorry, I keep saying a, but it's g this time, GHI. So we're going to turn that into a g. So minus 3g plus 2h plus I. And then kilograms is going to just be 1 plus g. Oh, this equals 0, this equals 0. We have no kilograms for the last two. And then seconds is going to be -1 again. Seconds is on the bottom. Nothing for g. H, we have minus h because it's on the bottom. And nothing for I, so that equals 0. So from this, we get g equals -1, and from this, we get h equals -1. Let me check that in my brain real quick. Yes. So then we can plug those in to this equation, and we get, I'm just checking to make sure my face isn't covering, -1 minus 3, -1, plus 2, -1, plus I. So now we can solve for I. So this is, I wrote it in a very difficult way to understand, -1 plus 3 minus 2, plus I. So -1 plus 3, that's 2, minus 2 is 0. So then I guess I equals 0. Alright, so cool. So then pi 3 equals, pi 3 equals the viscosity times density to the g power. G we said is -1, so that's going to be over density sorry, I'm like checking my work in my brain and then I end up not talking. So density to the -1, that means density is on the bottom. Then we have the diffusion coefficient to the h. H is -1, so it's also on the bottom. And then we have the diameter to the I, which is the 0 power, so that's going to be just 1. And so that's getting multiplied by 1 on the top there, but I'm just not going to write it. So, let me think about what's next. So I believe that hold on, let me think. I believe that this is the Schmidt number, and we are actually also looking for the Reynolds number. So since we're looking for the Reynolds number, we know that Reynolds number is we actually know. So okay, sorry, I was processing. We know that we are going to actually need this Peckold number, and we need the Reynolds number. But the Reynolds number is really just equal to the Peckold number over the Schmidt number, so pi 2 over pi 3. Because actually we know what the Reynolds number is, and we know that it has the velocity variable, diameter, viscosity, and density. So the only thing that we're kind of trying to eliminate here is the diffusion coefficient, which we can do if we just like put them on top of each other, because then they'll cancel out. So you can see it here. If we do pi 2 over pi 3, we have the velocity times the diameter over the diffusion coefficient over the viscosity over the density times the diffusion coefficient. So these are going to be gotten rid of, and it's going to end up being the velocity times the diameter times rho over mu, which we know is Reynolds number. I'll just rewrite it here since I kind of ran out of room. So we actually know that there is this Reynolds number included with the Schmidt and Sherwood number, and we know that we're going to have a relationship there. And so again, it's kind of working out how we're proving this. It's going to end up in the next part, we're going to kind of have do the same thing where we kind of like define the variables. So like it's going to be like Sherwood equals a coefficient times the Reynolds number to a exponent times the Schmidt number to an exponent. So you'll kind of see that play out in the next part. Alright, I'm going to pause this and go over to Python. Alright, so now we're going to move on to the coding portion here, and I just wanted to pull up what the directions were. We're going to generate 100 experimental data points by coding, so really they're pseudo experimental data points because we didn't actually run the experiment, from the given correlation with 10% normally distributed experimental error and for the data using this correlation. So we're going to do this by linear regression with Penrose pseudo-inverse and also by minimizing the sum squared deviation. So these are just like two different methods to solve this problem. And then we're going to plot the data and model it as 30 points and wireframe plots. So this can all be done within Python coding, so I'm going to go ahead and go over to that. First, we have our first block of code here, which I explained in past videos, but like always, we need to import numpy as np, so that's just going to allow us to have more complex functions that we can pull from in Python, and I'm naming it np just for simplicity. Then from plotly.subplots, import make subplots. So from that, we are going to be pulling in subplots, and we're going to make subplots. So that's the code for that, to plot our experimental data points. Then we are going to import our graph objects so that we can have more flexibility with how our graph looks. We're going to also import plotly.io as PIO. So PIO is going to be what's going to, like, our cosmetic changes to the graph. So we have Plotly dark is how we set up the template. Instead of like a white background, we're going to go with a dark background just so that the points pop more. And then from Skype.optimize import minimize. So we're going to get to this when we do that second method of the minimizing the sum square deviation between model and data. So we need the minimize function from the Skype.optimize library so that we are able to use that function to solve the problem. Alright, so I'm just going to run that just to make sure that it's run. There we go. So first, we are going to write out our equations for the Reynolds, Schmidt, and Sherwood number that we came up with when we were doing the written part. So yeah. Okay, so we need to do, I'm gonna type out Reynolds first. So Reynolds is gonna be equal to numpy dot we're gonna do uniform and then so numpy dot I feel like I'm forgetting something. Is it just uniform? To create, so we're trying to create a bunch of Reynolds number points. I feel like I'm forgetting something. The numpy random. I think there's a random. We can go ahead and Google it. We want a bunch of random points. I just don't know if it's a dot or an underscore. Numpy dot random dot, is it dot uniform? Samples are uniformly distributed. Okay, yeah. So, sorry, I kind of forgot, but numpy dot random dot uniform is what we're looking for. So we want to define our Reynolds number as a bunch of random points for our experimental data. So we have the low and the high and the size. So it's given here. The low is going to be the lowest number that the Reynolds number can be, which is 2,000. Our high is 35,000. And then the size is the number of points that we want between that interval. So I'm going to do 100 because that's what's given in the problem. And then we're going to do the same for the Schmidt number. So random.uniform. And then we know that the minimum is 0.6 and the max is 2.5. And then the size is going to be 100 as well. I wonder if it matters if there's spaces in here. I feel like it doesn't matter, but we'll keep it consistent. Then we're going to define our Sherwood number. So this is going to be let's go back to our notes. Oh, it's pulled up on the other screen. Just so that I can kind of remember. Yes, that's what we have to do. So this is going to be, let me take this back down, equal to the relationship, because now we have our Reynolds number defined and our Schmidt number defined. So we're going to just kind of type out that equation. So it's 0.023 times the Reynolds number, which we defined above, to the 0.83 power times the Schmidt number to the 0.44 power. I'm going to put these in parentheses just to make sure that it doesn't do anything weird. But that should be good. I'll just put these in parentheses for good measure. And then we're going to do the experimental error part. So we're going to have, so we just typed in the given correlation with 10% normally distributed experimental error. So to do the experimental error, we are going to do numpy.random, and then instead of uniform, we're going to do normal, because it's like, if you think about all of the data is on a normal curve, it's more likely to be towards the middle of the data, like the mean of the data, than the outside. So we want it to be on a normal curve so that it considers the error, like, but it's still more likely to be correct than just uniformly spread out, if that makes sense. So in this case, we have our Sherwood number, and then our error, so which is going to be 10%, so 0.1 times the Sherwood number. So it's going to give us a bunch of Sherwood numbers with 0.1, or with a 10% error, which is 0.1. So we're going to go ahead and shift enter on that. Great. Now I'm going to actually, on my whiteboard here, kind of show how to do the next part. So let me pull up my camera so that I can see my camera is, or like where my camera is down here. So I have this little whiteboard, and I don't want to like, oh, it's going to be backwards, isn't it? Well, maybe that's not the best idea. Maybe I'll pause this and flip it, and then I'll explain it. Sorry. Alright, so I made myself bigger, and I also flipped the camera, so now you can see, like, you can read my whiteboard. I just, since this is kind of a quick explanation in the middle of the code, I didn't want to like fully switch over to my tablet and everything. So I'm gonna just like explain how to do the Penrose pseudo-inverse method by like manipulating the matrices, and yeah, that's our method for our linear regression. So I just wrote that here, like I showed you. But we have our Sherwood, Sherwood correlation with our coefficients. So I'm just going to write that out, and then I'll show you what I mean. So this is what I mean by the correlation with the coefficients and the exponents as variables. Which is what we're trying to figure out what those are by using this code, what the A, B, and C are. So in our linear regression, we're just going to do the natural log and I'll show you in a second what I did. So as you can see, I just did the natural log of everything from that relationship. So now it's natural log of the Sherwood number equals natural log of A plus B times the natural log of the Reynolds number plus C times the natural log of the Schmidt number. And then next we are going to put this all into a matrix. So here's our design matrix, and the first column is just going to be ones as our base here, and then we're going to do, sorry, my camera is down here, so I keep making sure that I'm in frame, because my my monitor, anyway, it doesn't matter. So then we're going to do the natural log of the, let me just write this down, Reynolds number and the natural log of the Sherwood number, or the Schmidt number, I'm sorry. And then that's going to be a column like this. And then we're going to multiply that by an unknown matrix, U. And this is going to be where we get our unknown variables, the ABC. So that's going to have natural log of A, natural log of B, natural log of C. And then that is all going to be equal to a matrix with one column with the natural log of the Sherwood's number. So that's kind of what the matrices look like. So after that, I'm going to simplify this and call it X, matrix X. And that's going to be our design matrix. So we have, it's just going to simply be X times U equals the natural log of the Sherwood's number matrix here, like this. And then to get our symmetrical matrix, we need to just multiply both sides by the transposed matrix of X. So it's going to be like this: X transposed times X times U equals natural log of Sherwood times X transposed, like this. And then we can just simply, to get the unknown matrix by itself, the U by itself, we can just multiply by the inverse of that transposed X times the X matrix. So it's going to look like this. Just like this. So I hope that's kind of clear, but I think it'll make more sense when I code it out. I just wanted to, for my understanding, kind of do that out on a little whiteboard so that when I code it out, it all makes sense. So I'll just kind of show what it is here. Alright, so now let's go back to the coding. I believe my face is like over here, so it shouldn't be blocking any of the coding. So we're gonna first do np.column stack. And the reason why we're doing this column stack is because it can take, here, I will explain it here, a sequence of 1D arrays and stack them as columns to make a single 2D array. So basically we can just put in our columns and then it'll make it an array. So for our column stack, we are going to first have that ones column using the ones like function from NumPy. So ones like, oops, and like it says, it just returns an array of ones with the same shape and type as a given array. So our given array is going to be Sherwood Then we are going to do our next column in the array, which is according to this. We did the natural log of the Reynolds number, so log of, I think we have to push it, np.log, maybe not, but it works that way. np.log, this says natural log, so that's what we want, and then our Reynolds number. And then lastly, we're going to have our np.log of the Schmidt number. Alright, I believe that's all correct. So then, what do we do next? Then we are going to do, oh, we need to define U. Actually, let's call this something. Let's call this X our design matrix, this one here. And then we also have our U, or unknown matrix, to find those A, B, C, the coefficient and the exponents. So that's what's going to be our unknown. So let's define that as U, and then we can do our inverse function. So since we have, well, there's kind of like a couple ways that we could write this, but we need our inverse function, which is from the NumPy library, and we need to do the linalg for our linear, because we're doing the linear regression, and then it's the inverse, so it'll tell us what it is here. Computes the inverse of a matrix. So since we did the inverse of the transpose X times X, we can do X, which we defined, dot T, is it a lowercase t? Let me look up Python transpose transpose matrix. I think you just do dot T. This says matrix dot transpose, but what if I want to do, oh, here we go. Array property returning the array transpose. So yes, it's a dot capital T. So I'm going to do that, and then we are multiplying that. So I believe multiplying matrix is an @ symbol. Yeah, and then multiplied by X. So we're doing the inverse of that, which is here on our sheet. And then we're going to do multiplied by the transpose X. So how do I write this? So this is outside of the inverse. So then I guess we'll do the @ outside. And then X dot T again times the natural log, I'm looking at my whiteboard here, which is going to be numpy.log. Wait, is that right? Yeah, it was a Sherwood number. Let's see if that works. So let's see if that works, and do print, and we're going to print U, and we're going to print U with, since we did the natural logs, oops, I don't know what just happened there. Natural logs, we need to do the exp, the exponent, of the first element in that list. So U is 0. Let's see if that works out. Alright, sorry, my roommate came in, so I had to pause real quick, but This method works out, we can see, because the 0.844 is really close to 0.83, 0.429 is really close to 0.44, and 0.02007 is really close to 0.023. So that's just one method that we can use. They're going to be slightly different numbers because there's different methods, and we're using experimental data here with a 10% error. So now I'm going to show the other method, which is the minimizing the sum squared deviation. So that was the pseudo-inverse method, but now we're going to do the minimizing the sum squared deviation method. I like this one. It's basically you just define the function of sum square, then you sum, you summarize the squares of the correlation here, and then you use the minimize function from the Skype library, and use the initial guesses essentially, which is the values here, the 0.023, 0.83, and 0.44, and then you'll see that we'll get an array with numbers that are similar to these ones here. So let's go ahead and do that. So first we're going to define the function. You can call it whatever you want. I've been kind of calling it different things. I'm just going to call it sum square for simplicity. Then I always just choose a letter. I'm just choosing F. Just because then when you call on like a specific element, so like f of 0 is the first element in the array, then you only have to type out one letter. That's why I do that. So then we're going to return numpy.sum. So like I said, we're summing this correlation here, the equation. So it's going to be Sherwood minus f of 0, which is the first because of just how it indexes. It starts at 0, it's the first element, times the Reynolds number, times, to the double asterisk is exponent, to the second, sorry, there we go, and then, so that's the second element, and then times the Schmidt number to the power of the third element, so that's going to be 2. And then we're going to square, so we need an extra parenthesis here, so we're squaring all of that, so double asterisk 2, close it up. Then we're going to use our minimize function from the Skype library that we imported, like I said. Type in the function that you called it, minus sum square, and then our like initial values for our like x naught, which we're going to use the known values, which is 0.023, 0.83, and 0.44. That looks good to me. Let's shift enter, and you can see in the x array here we have the values that are very similar to our known values. So 0.0238 is really close to 0.023, 0.826 is really close to 0.83, and 0.435 is really close to 0.44. Stop the recording now. Alright, so now that we have all of that working, we just need to graph everything. So we need to plot it all. That is the last instruction in the part 2 here. It says plot your data and model as 3D point and wireframe plots. So we have all of our 100 pseudo experimental data points with the 10% error, and we want to plot all of that with our Schmidt, Reynolds, and Sherwood grid. So I'll talk about that more when we get into it, but first we need to just name our plot, so we can just call it fig, short for figure, and And then we're going to make subplots, which we pulled from Plotly at the beginning. Then we're going to do fig.add trace to define to pull in the graph objects, and then we will define what our type of plot we're making. So graph objects from Plotly is, we called it go. So I'm going to pull in go, and then I'm going to do scatter 3D, and I have a bunch of my Google pages up here from my last take, but I'm going to make sure that it's a lowercase graph object dot scatter 3D. I'm just making sure that it's a lowercase d, which it is. So that's correct. And then we're gonna do x. We're gonna just like define which dimension this number is x, y, and z. So x is gonna be our Reynolds number, y is our Schmidt number, and z is our Sherwood number. So that looks good. And then I'm also going to define the mode, which is going to be markers. And if we want to change the size of the markers or anything like that after we look at it, we can do that here. So the markers being the mode, it's just, that's going to be all of our individual data points, whereas later we'll do the mode equals lines to make our like wireframe. Okay, so that looks good. So next we're going to do our Schmidt grid. So I'm going to call it Schmidt underscore grid, and this will be our Schmidt like points on the plot. So this is going to be equal to numpy dot, wait a second, oh, mesh grid, yeah. So I'm going to look that up to make sure I know what I'm looking at the right thing here. So numpy.meshGrid returns the coordinate matrices from coordinate vectors. We can even go to an example here. So some of these things are optional, but with numpy.meshGrid we need our xv and yv equals xy. So we're going to have the Schmidt grid and the Reynolds grid here, and then we're going to have our Schmidt and Reynolds grid, what they're equal to in the parentheses. So I'm going to go back to my code. So we're going to do Schmidt grid, comma, Reynolds grid. Glad I looked that up because I forgot about doing the comma. And then we're going to do numpy.meshGrid. And then we're going to do numpy.linspace because we are going to return evenly separated. Here, I'll pull the official definition up. The official definition is return evenly spaced numbers over a specified interval. So our intervals we know for Schmidt, it is 0.6 to 2.5, and our number of points that we want, we can just do 25. You can kind of make it whatever looks good. since we weren't given a certain number that we needed. And then for Reynolds number, it's going to be, we know, from 2,000 to 35,000, and we can do the same number of points. So that looks good. Next we're going to do, oops, didn't mean to run it yet. I accidentally clicked Shift Enter instead of just Enter. Next we're going to do the Sherwood Grid and define that. So that's going to be numpy.r.exp because we did the like natural logs in our equation from before. So that's going to be u, the first element in u, which is actually 0, not 1, times Reynolds, and this is going to be grid, I believe, to the power of the second element in u, and then times the Schmidt grid to the, oh, I messed that up. There should be a 1 for the second element, there should be a 2 for the third element. 2. So that looks good to me. Then we are going to do a for loop. So we're going to use zip, which is like a function that comes with Python, and this will help us create our lines because it's a for loop. So we can call our 3 different like variables something. I'm going to call it I, J, K because these 3 letters are like used when you're working with matrices. So that will make sense here. And so we're going to do for I, J, K in zip. Oh, here we go. So zip returns a zip object whose next method returns a tuple where the ith element comes from the thing continues until the shortest interval. That is the second. So we need our arguments. So we're gonna do each of our 3 numbers as our arguments here. And then, I don't know if it matters if there's an indent there. If we get an error, we'll know. We're going to do fig.add trace because we want to make our lines now. So we're going to do go.scatter 3D. And then define our x, y, and z this time as x equals I, y equals j, and z equals k. And then we can do mode equals lines this time. Mode equals lines, since these are going to be our lines. And then I'm going to also make the line color, line color. Let me look up the function for that. Line color in oops, didn't mean to. this just says color. Let's see if that works. And then if we get an error, we can go back to it. Oh, I need to say what my line color is going to equal, which is white. And then we want to plot or output our figure. So let's run that and see what happens. It says make subplots is not defined. I'm going to go ahead and run through these. I actually left, in case you can't tell by the lighting and my outfit, I left and came back, so I think these might need to be rerun. There we go. So now that's not the error, but we have an error somewhere in here. It says odd trace got an unexpected keyword argument mode. Oh, I see. So it's not supposed to be an odd trace. I believe it should be like this. So I'm going to change that here as well. The parentheses should be way on the outside. Let's try that again. Great. So we have our plot. It's not beautiful yet. And also there's something I think going on with our z. Z is equal to 0. So I'm going to move on to what I think I need to do next, and hopefully it'll fix itself, and if not, we'll come back. So next we need to just copy and paste this, but do it with the Reynolds and Schmidt number reversed, because we need to do, we need to consider both. So we're just going to flip these. And then the rest looks good to me. Shift enter that. So now we have the lines going the other way, which is good, but they're still on, we still have a z of being equal to 0. I know what the problem is. It's only the exponent, or the e to this. The parentheses I put way on the outside for some reason. But that makes sense. So let's try that. So now we have non-zero numbers, that's amazing. And we can plot our fig. Great. So, after several minutes of problem solving in my brain, I think that we finally have our grid, our wireframe grid here, it looks great. There's some other things that we can do to it to make it look even better. All of these trace things on the side are not preferred to have there, and it would be nicer to have Reynolds, Schmidt, and Sherwood instead of X, Y, and Z. And our data points might be a little large, so if we did marker size equals, I'm not sure what the, let's say 3 and see what that does. So that makes it a little smaller. Even possibly a little too small, but I'm just going to leave it at that for now. It kind of just depends on what you care more to look at, how much you care about each little individual data point. And then we can also, what was the other things I said I wanted to do? Kind of just update the layout. So we're going to do fig.update underscore layout. Pretty easy to remember that one, because that's exactly what we're doing. We could adjust like the height and such if we wanted to. I guess we can go ahead and do that. Let's do like 900 and 900. You can kind of, again, adjust it how you wish. And then we're going to do show legend equals false. I wonder if that's, okay, I don't think that you need, is it show legend? I feel like usually it has the underscore. Show legend equals false. And then dictionary properties we have to hit, yes. So then we're going to do scene equals dict, like it says here, and this is where we're going to do our axis titles. So the x-axis is going to be Reynolds number, the y-axis title is going to be the Schmidt, and z is going to be equal to Sherwood. Oh, with quotes. Let's shift into that, see how that goes. Oh boy. What went wrong here? It looks like it's giving the whole dictionary. Why won't it let me scroll up? There it goes. It says I wasn't sure about this one, so let's see what happens there. Oh, good. So we might have made our plot a little bit too large, but it's looking pretty good. So now we have our axis titles. We have it a little bit bigger. I think I would make the marker sizes maybe a little bit bigger if I felt like it, and I might make the whole graph itself a little bit smaller, maybe 700 or so. go ahead and do that. But overall, it looks pretty good, and that is our final answer. So, yeah, I'm going to stop this video now. Where's my OBS? There we go.